Thank you very much. Welcome, everybody. We're excited to be here. What we will talk about today is a collaborative effort between three different parties, and I'm really happy that we have all of them on stage. So with me is Chandan, who's the quantum chemistry lead at BMW, was directly involved in this work. We have then Anand Shah from Quantinuum strategies, and myself, I'm working at Airbus, coordinating and managing the quantum portfolio. So BMW and Airbus, we are both active in the mobility sector, and together we are covering quite a large part of the relevant portfolio, and we have similar challenges. And one of those challenges, and it's actually driving at the moment, is how can we achieve decarbonization? How can we achieve low carbon mobility? Today, just try to go to the next slide. Yep. There we are. So today, our products, they contribute to global warming, actually over the full life cycle, so meaning in the production, but also in the operation of the vehicles. And actually, specific in mobility, the operational part is quite high. So for example, for an aircraft, more than 99% of the CO2 emissions are produced during the operation of an aircraft and not in the production or recycling part. So both Airbus and BMW are committed to reduce carbon emissions to achieve decarbonization of mobility. And we're actively looking for technologies to achieve that, and also including quantum computing. One of the technology you probably know is electrification. So in particular in the context of cars, this is very prominent, but there are more technologies. And actually there is not one silver bullet to achieve that. Today we will talk about hydrogen. So how can we use quantum simulation to accelerate research in hydrogen? So just to put this in the context of what we do in general in quantum computing, this is one of the typical clusters being pursued, which is quantum simulation. We're also looking, for example, into materials. Other problems in the mobility sectors are around optimization, mostly combinatorial optimization problems. Machine learning is very important for us, for example, for generative design, but also for data analysis. And a key topic in mobility is also solving equations, in particular nonlinear partial differential equations. So today we will talk about a specific topic in hydrogen, and just to give you the context why hydrogen is important for aviation and what we are doing. So at Airbus, we believe that hydrogen is one of the core technology bricks for decarbonizing aviation. And we are pursuing this path with our ZeroE project. So in this project, we are developing different configurations, different technology bricks, and also we are creating and preparing the overall ecosystem around hydrogen, because we need a supplier of the hydrogen in the end also to operate those aircraft. What you see here on this slide are different configurations which are currently investigated. You see some of them are classical single-aisle aircraft. We're also looking into blended wing design, for example, which is very interesting for hydrogen. And we are talking here about passenger capacity of 100 to 200 passengers and about a range of something like between 1,000 and 2,000 nautical miles. So the objective here is to bring the first commercial hydrogen-powered aircraft into the market in 2035. There are many challenges. One of the challenges is, of course, how do we power those aircraft? How do we design the engines? And there are basically two options. You can either burn hydrogen, or you can use fuel cells. Fuel cells to convert hydrogen then into electricity. So this fuel cell powered version is actually very interesting. Why? Because, of course, if we have green hydrogen, then we are not producing CO2. We are also not producing NOx. But there's another example. Hydrogen fuel cell powered engines are producing none or nearly none condensation trails. And these condensation trails actually contribute quite significantly to the global warming effect. So you see here a sketch of one of our models. In the middle, you see the fuel cell stack, this yellow, blue block. Those fuel cells are not commercial products which we can just buy. So Airbus has recently found a joint venture with Elring-Klinger, which is an automotive fuel cell provider. We have done already some ground tests in the megawatt regime. We will test this engine first time in 2026, attached to an A380, and all with the objective to bring then the aircraft itself into the market by 2035. So what's so challenging for the fuel cell? The fuel cell needs to have a very high power density. Why? Because we need to bring an aircraft into the air. We need to let it travel for maybe 1,000 nautical miles. So what does it mean? If we have too heavy fuel cells, then it just doesn't work. So one objective for us is to increase the power density here. And this is also linked to the study which we present to you. So then I'm happy to hand over to Chandan, who will tell us about hydrogen and BMW.
Yeah, thank you, Jasper, for introducing the aviation challenges. So, I would like to quote from our CEO at BMW Group. When it's more scalable, hydrogen will be hippest things to drive. And this is the motivation that in addition to having electric vehicles in future together we add alternative energy sources. And one of those solutions would be fuel cell. So what you see on the slides, this is a car, this is a fleet of hydrogen fuel cell that's already being tested. And we already have some exciting results from the industry that fuel cell would be a promising solution in the upcoming years. So that's the motivation from the automotive sector that fuel cell car would be addition to electric vehicles, and that will lead to this decarbonization steps for the mobility industry. So going deeper in the topic, I would like to introduce you how the fuel cell system looks like for the automotive, for the car, and what Jasper also introduced, the picture in the left down is from the aviation. And what you see on the top in the left is a fuel cell in the car. And the next step, what you see is fuel cell stack. So meaning you have a single pouch fuel cell, a single fuel cell stacked together, and then it makes the energy source for the powering the car, producing electricity. And in individual single fuel cell, what you have is this schematic, that catalyst, and also the carbon-supported platinum particles. So this platinum-supported catalyst is our interest. So one of the key reactions that happens is the oxygen reduction reaction. That's what we are most interested in. So it's one of the key steps for the catalytic conversion, and it has challenges. So the challenge would be having a high barrier. And also, we would like to understand the barrier for the platinum system, but at the same time, using quantum chemistry and quantum computing, we would like to see the effect of introducing cobalt for this carbon-supported platinum particles. So what I meant by introducing cobalt, so in this particular project, we started with a layer of platinum, and then we would stack cobalt to see the effect of the chemical reactions. So in next slide, I show you the schematic, how the cathode material looks like within fuel cell. And as I mentioned, the efficiency depends on the kinetics of the oxygen reduction reaction, and kinetic itself depends on the energy gap for the transition states. And this is a very challenging problem to compute the energy gap very correctly. And in classical simulations, like for example DFT, there has been studies to compute this energy gap for transition states. As I also mentioned, the reductive dissociation of O2 is the rate determining, so meaning it will really change the efficiency if we have better understanding of the O2 dissociation that's happening on the platinum surface. And for us, we started this study with classical simulation to understand how the system, platinum and cobalt look like. And I would like to show you one of the results that we have. So as I said, the stacked system, which is the platinum, what you see in the left. So a stacked layer of platinum, 5x5 system. And in the second picture, the system is where we have only 2 layers of platinum, and which is then a layer of cobalt. And this is the classical studies. So in order to understand the electronic structure of these systems, you have to perform a DFT calculation to see the geometry, or to have an optimized geometry. So in this study, we started with first pure platinum, and then looked into the reaction path, how the transition states look like. And what you see in the left is for pure platinum, and in the right, what you see is for the mixed platinum and cobalt. To emphasize here, in the left, you see 2 curves, so meaning it's reflect 2 pathways to dissociation. So you start with O2 on platinum, and then one dissociates in the symmetric, and then one is asymmetric as trans. So for the nickel system, it was really difficult to obtain the transition states. So there are some effects, for example, magnetization, that plays role when we have cobalt. And this makes the electronic structure calculation from the classical DFT quite challenging. So to incorporate this effects, what we call correlation, we would like to see, we would like to go beyond DFT. And in order to do those, I would, in this project with Quantinuum, we also have this quantum workflow that tackles this challenge. And I would like to ask Anand to introduce the workflow for the quantum project.
Thank you, Chandan. So as Chandan mentioned, quantum chemistry methods are used to understand how these reactions take place on catalytic surfaces, and also to calculate the reaction kinetics of these reactions. So what we developed was a hybrid quantum classical workflow to model these reaction pathways. So we first started using density functional theory, so purely classical, to perform geometry optimization. So we first calculated the initial states, which would be the oxygen molecule absorbed on a catalytic surface, and then the final states, which would be the 2 oxygen atoms dissociated, still absorbed on the metal surface. And then using the nudged elastic band method, we were able to then calculate the transition state, which is the highest energy saddle point in your reaction pathway. So then once we have the geometries, we can actually calculate the energies. And we can do this, again, using a classical method like DFT, or we can actually calculate these energies on a quantum computer. And so this workflow was conducted using Quantinuum's InQuanto computational chemistry platform. And for the quantum simulation, we implemented the variational quantum eigensolver. And then to further improve our accuracies and results, we added additional extra energy correction terms to address second-order perturbation theory. And doing that, we obtained even more accurate results. And what I show here are the results of the pure platinum system. So first, you see the DFT benchmark result, but then you also see the results from, if the slide will progress, from the quantum simulation. So first, starting out with a noiseless state vector simulation, as well as a noisy emulation, and then finally, the actual hardware experiments performed on the Quantinuum H1 machine. So what we found from the pure platinum system is that we can work with pretty small active spaces, ones that we can fit on today's quantum computers, so active spaces of 2 electrons and 3 orbitals. And these reproduce the activation energies that you can calculate with DFT to a great level of accuracy, and they reproduce these trends pretty well. But actually, as Chandan was mentioning, the platinum cobalt system is the one that has a more complex electronic structure, where you have some challenges on the DFT side, but also on the quantum side, we found that small active spaces actually provided a negative activation energy, which is, of course, not what you want to see. But as you started to increase the size of those active spaces, at least out to 8 electrons and 8 orbitals, something that doesn't fit on current generation hardware, but you would be able to see a reversal in that trend and actually start to see positive activation energies. So I think the key takeaway here is that for systems that do have complex electronic structures, like the platinum cobalt system, we do need to actually evaluate these on quantum computers, but for that, we will need to be able to implement larger active spaces than possible today. So with that, I'll pass it back over to Jasper to add some concluding remarks.
Yeah, thank you very much. So to conclude, so I think the key message we wanted to convey is that we believe quantum simulation matters for mobility. So of course, there are many hurdles to overcome, but we still believe it's a chance to use the results of quantum computing early to achieve advantages. And I hope we could also convince you that these advantages are not, let's say, only on an academic level. They have a real impact potentially on our future. So if you have any questions, we are going to be around today. Also, please feel free to reach out to us. And since we have still, I think, 1 minute left, I would like to use this one to just re-announce, or for those who didn't see that yesterday, we announced yesterday between BMW and Airbus a new quantum computing challenge. Airbus has performed already one in 2019, then BMW in 2021. And so now we have combined our initiatives in this challenge. And one of the problem statements is in the area of quantum simulation. The quest is there to to investigate quantum computing for corrosion inhibition processes. And we would appreciate very much if you have a look, go to the landing page, and if you're interested, then please register and join this challenge. Thank you very much.